So yeah, I guess we can get started. So let me start the slides. So I'm going to talk about machine reading with neural networks this time. And what I mean by machine reading is basically read a passage and try to answer questions about that passage. So this is in contrast to knowledge-based QA, which is kind of the stuff that I talked about during the semantic parsing stuff and the semantic parsing class and the in last time. So basically, the passage is a knowledge base that you need to use. It's a textual knowledge base, but it's a knowledge base that you need to use to answer the questions. So there's a bunch of these machine reading tasks. I think there's kind of a couple varieties of them, specifically multiple choice questions, span selection, and close fill in the blank style questions. And kind of these aren't completely mutually exclusive. You can have a few of each, but just kind of in the general framework, you have these kind of three things. So there's a lot of different data sets for this. For example, MC test is 500 passages and 2,000 questions about simple stories. They look kind of like this, where you have James the turtle was always getting into trouble. Sometimes he'd reach into the freezer, et cetera, et cetera, et cetera. And then you need to get to the end and you need to answer a multiple choice question. So this is kind of like the thing that I talked about before, where you need to finish a story, but instead of finishing the story, you need to answer questions about the story. Another one, which was done by people here at CMU, which is very interesting but also extremely hard, is the race dataset done by Chiza and others. It's 28,000 passages with 100,000 questions from English comprehension tests. If you look at the data for this, it's super, super difficult. And we've done a little bit of work on this, and you can barely get above chance accuracy on this data set if you consider chance as a model that doesn't read the passage and just looks at the answer. So if you just look at the answer, you can get about 41% accuracy on this data set. And if you look at the passage and the answer, you can get about 43. So this is good if you want a challenge for things to look at. Yeah. There's also span selection ones. These are really, really popular nowadays, especially Squad, which I think a lot of people have heard about. So they also, this Squad basically is Wikipedia articles with questions, and then you need to select a span from within the Wikipedia article to answer the question. This kind of makes things a lot easier because you're guaranteed that at least somewhere in the article is going to be the question. So unlike the multiple choice questions here, these questions might have something that doesn't even match the question at all, and then you need to kind of infer from this. So I think people might have seen. Yeah, sorry, go ahead.
So are the questions framed in a way that the system does not require any external knowledge bases? So in the previous example, I saw, like, did the turtle get in trouble or something like that?
Mm-hmm.
But then the system has to understand that trouble is not a room; it's a verb, or it is a noun.
Yeah. So my understanding is that you do need external knowledge for stuff like this. You need external knowledge about that's kind of common sense, but or maybe not even common sense. You need external knowledge at the level that an Amazon Mechanical Turker has. So, for example, you might need to know that the Denver Broncos are a football team, which not even some Mechanical Turkers might not know. But, the important thing is that the actual answer to the question is within this passage. And that's interesting. That's an interesting question because that also means that you have to do stuff like use word embeddings that were trained on large amounts of text that allow you to take that into account, or whatever other way of incorporating external knowledge. Any other questions about this? Okay. There's also the Trivia QA data set. So this is another interesting data set. 95K questions in 650 evidence documents. So this one, you don't actually know which document, or I think you don't know which document the answer is in, and you kind of need to, or actually, sorry, I'd have to confirm that. But you either don't know where it's in, or they've retrieved documents that it's in for this one. But basically, you have multiple other documents, and you need to find the answer within those documents. So for closed questions, there's also a lot of examples. Kind of the first thing that sparked this whole interest in neural networks and machine reading is the CNN Daily Mail dataset. This was created from summaries of articles. So you have a news article from CNN or the Daily Mail, and both of these provided you with a summary of like 5 sentences. And then they took an entity in the summary and they blanked it out to make a closed question, and then you had to guess which entity filled in the blank. So I think most people have moved on from this data set. It's not the major data set that people are using at the moment, but it was very influential in kind of sparking the interest in neural models because it was the first kind of really large scale one. So here's an example of what it looks like. They also did a couple other things, like they took the entities and they anonymized them. So they didn't want you to say, so here's an example of a query, like producer X will not press charges against Jeremy Clarkson, his lawyer says. If you just trained a really big language model, you might be able to guess which entity in here was a producer. So basically they anonymized the entities to prevent you from doing that. So if we think about what's necessary, yeah, go ahead.
So by anonymizing, you mean that the same entity 212 refers to Jeremy Clarkson in all the documents, or do they shuffle this around?
It refers to Jeremy Clarkson only in this document. So it doesn't. They don't do it. I'm pretty certain that they don't do the same one across all the documents, and the reason is precisely that. You don't want it to learn a language model. Any other questions? Okay. So as an aside, actually, there's another data set that I forgot on the slides, which I believe is Quasar. By Bhuvan Dhingra and others here at CMU. In this one, they don't anonymize anything, and it turns out training a really strong language model actually is a very good baseline on this data set. So if you care about closed questions, or you care about questions that can be answered by a language model, a language model as a source of information is actually very useful. So what is necessary for machine reading from a neural model perspective? Of course, common sense knowledge, being able to match things that mean the same thing but are written in different ways is very important. But some other things that will kind of be the focus here is we need to be able to take in a large amount of information, specifically the document, and extract only the salient parts. And this is basically what attention does, right? We have a large, long sequence, and it picks out the part that actually makes sense. And there's a lot of methods for using attention. And another thing is we must perform some sort of reasoning about the information that we've extracted. So, for example, multi-step reasoning. This also becomes very important here. So I'm going to talk about some methods that people have used for both of these. So any questions so far? Okay. So now I'll walk briefly through some models that people have been using. The important thing here is now we kind of have 3 things that we are interested in handling. We have a document, which gives us our background knowledge. We have a question that's asking about that, and then we might have an answer. So in the case of span selection or close, we might just need to attend to somewhere in the document. In the case of multiple choice, we might need to attend to all 3 of them. So a very, very basic model for document attention. And encode the document in the question and generate an answer in the form of a sentence or a single word. So basically, you take the document and the question, and you encode it, and you predict the answer. And of course, the problem is encoding whole documents with high accuracy and coverage is very hard. So it's just coming up with attention over the document without any sort of kind of prior knowledge about the question is not going to solve all of your problems. So a first try to kind of mitigate this problem in a way is called the attentive reader. The way it works is you read the query or the question first, and then attend to the values of this. So basically what you do is you encode X visited England. So you encode the question, and based on your encoding of the question, you then select which parts of the document to attend to. So this makes a lot of sense, I guess, if you think about how you answer questions on tests. You read the question first, and then you read the document looking for the information that would help you solve the question, right? So that's precisely what this is doing. And these attention things on the left side of the model basically allow you to focus on the relevant information. The one thing here, though, is you're still creating a representation for the document without knowing the question itself. So you create the representation for the document first, and then you just attend to the relevant parts. So they had a second model here called the impatient reader, which basically rereads the document every time you get a new query token, and updates your understanding of the document. So what it does is first you look at X, and based on X, you do attention over the document and generate a representation R. Then you take in visited, and then you reread the whole document, and you create another representation R. You take in England, then you reread the whole document, and you make another representation R. And this is all within a recurrent neural network. So this is starting to get a little bit not like what we expect that we're doing when we read, right? Yeah, go ahead.
What exactly do you mean by rereading?
Well, reattend to the whole document might be a better way to say it. So you have a different combination of you have different attention weights for each of the words in the query. So one thing that you can think about is this is very similar to a, let's say, it's kind of like a multi-step reasoning model where the number of steps is decided to be the number of words in the target question. So I'll be talking about multi-step reasoning next, so you can kind of think about this model in that way as well. Yeah.
There is also final query embedding at the end.
G, yeah, so this is the thing that they finally used to answer the question, I think.
Okay, so you take in each word and attend to some relevant parts, and then finally look at the entire query as well.
So your encoding of the query R, is your final one here, is basically what you've done after you've done this recurrent process through the number of steps equal to the number of questions. So these were both models that were tested on kind of the CNN Daily Mail dataset, and they were used to predict the entity X. So another model that has been used to solve these problems is called the attention sum reader. And basically the idea is instead of attending to get the representation, you instead you instead attend to each entity in the source document, and you use the entity that gets the maximum amount of attention as the answer to your question. So basically the way this looks is you have a, it's a little bit hard to read here, but Obama and Putin, something, 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 said Obama in Prague. So you see Obama appears 2 times. We have XXX visited Prague, and we encode the question, and then based on this question, we attend to all of the entities in the document. And then the score of each entity is basically the sum of the scores over all the mentions of that particular entity in the document. So this model is actually relatively simple, but one of the good things about it is if there's a bunch of different mentions of a particular entity, you are likely to pick up on one of those, one of those various mentions to be the one that actually makes the difference and makes it so that you know the answer to the question. So, of course, said Obama in Prague very strongly indicates that Obama is in Prague. So this one gets a lot of attention. Yeah.
So if there are a lot of mentions of a specific entity, would that kind of encourage us to select something that's mentioned very often?
Right. So you could definitely argue that that would be a weakness of this model. It's a strength and a weakness of this model, right? So if something's mentioned a lot, it's probably going to come up in a question. It's also a weakness of the model is it might overgenerate frequent things. So I actually don't know if they took a look at that in the paper. I don't think they did, but that would be interesting to see. Yeah.
Are any of the questions in the dataset, like do any of them require an APRA resolution such that this model wouldn't be able to recover it without having a equally strong co-reference model?
So do any of them require an APRA resolution? That's a really good point, and I'm pretty certain it did not do that, but I'd have to go back and take a look at the paper for sure. As I said before, there are papers that use co-reference resolution in encoding for question answering, but I don't remember what the attention on top of that model was. It's definitely something that's really, really important though, because especially if you have, children's books or something, it's just going to mention the name once, and then it's going to say she and he for the rest of the stories. So, yeah. Okay. So there's another method called attention over attention. This paper had nice results, which is a good thing about the paper. Also in their abstract, they said, as far as we know, we were the first people to do attention over attention. I don't know if that's a really strong argument for the novelty or impressiveness of your paper, but hey, maybe they were the first. But the idea is basically that we want to know the words in the document that were most important for the important words in the query. So it's kind of a double. You want to know which words are important in the query, which words are important in the document, and you want to use both of these pieces of information to answer your question. So the model basically looks like this, where you have your document, you have your query, Mary sits beside him, he loves Mary, and then you have he loves X. So you have one variety of attention that basically says which words in the document match each words of the query. Then you have another one which says which words in the query seem important for the document on average. So maybe he, or maybe X is important or something like this. And then you basically take the column-wise sum or column-wise average over the words in the query to kind of get an importance score for the words in the query, and then you take the attention. You multiply this and take the weighted average of the attention, which gives you which word in the document is the most important one. And then you combine this with the attention sum reader, which basically tells you additionally which ones are important. In the query. So I'd say this is a pretty good model to use. There's a bunch of more complicated ones as well. If you go through the squad leaderboard, you can see, you know, lots and lots of examples of more complicated models that do slightly better. Are there any questions about this? Okay. So I'll go to the next part, which is specifically for span-based question answering. Actually, I kind of feel I made the first draft of these slides last semester. I kind of feel like the community is slightly moving away from span-based question answering. Like people are Squad is becoming a little bit less popular and people are branching out to other data sets. But still, I think choosing spans is really useful if you actually use Google and try to ask it a question. It will give you an answer, and then it will also give you the span that it extracted it from. So obviously, they're doing something inside of this for their question answering system as well. So up until now, I was talking about word classification or entity classification, which assumes that you have a single word or entity that you want to classify. So in span-based models, you need to basically choose a multi-word span, like within a cloud. In the previous single word models, we're basically choosing a single word or entity. This is in contrast to NER, where NER basically needs to choose multiple spans. So it's not just a single span. You need to choose every span that's an entity. So this one will choose a single span within the document that gives you an answer. So one example of a model that does this is the bidirectional attention flow model. And you basically calculate attention from the document to the context in the context of the document. So here context is your query. And then both representations are concatenated to word representations themselves in the document. And then based on this, you try to classify the beginning of the span and the end of the span. So the idea here is basically you have attention in both directions. So for each word in the for each word in the document, you attend to the words in the query, and you get your representation of the query based on that word. And then for each word in the query, you attend to words in the document as well, and sum over. So, concatenate them, and then you feed this into a BioSTM and choose the beginning and end. So basically, you're trying to train a model that classifies the start and the end of the span. And this is a particular model that used to do that.
Question.
Yeah.
So, what are the predictions start and end? Are they like integers that denote the position of the span, or?
Yeah.
And how do you enforce constraints like the start value has to be less than equal to the end value?
Okay, so that's a good question, and in this case, if I remember correctly, they just predict the start, and then they predict an end that comes after the start. I think they're doing something like basically that simple. The next thing that I'm going to introduce does it in a little bit more elegant way. So the next one is a dynamic span the dynamic span decoder, and basically what this is doing is it's iteratively refining the left and right boundaries. So what you do is you basically have your model that allows you to predict the start, and then you have one model that predicts the start, and then based on the start you predict the end, and then based on the end you predict the start again, based on the start you predict the end again, until basically it settles down and you have the start and the end. So this is the slightly more intelligent way of doing this. So anyway, So that's all for a span-based thing. And now the part that I particularly find more interesting, or more kind of more essential to the task of machine reading than the attention part. But the attention part's really important to get right also. But it's the idea of multi-step reasoning. So one thing is that in machine reading tasks, and actually kind of AI tasks in general, it often becomes clear that more information is necessary post facto. So if we say John went to the hallway and John put down the football, and then we have the question, where's the football? Obviously, the first thing you're going to do is you're going to look at football, right? Because where's the football? And then you look at the sentence that has football, you see John put down the football. And so you attend to John and say, okay, now I want to know where John was, or where John is when he put down the football. And then you attend to John and you see John corresponds to hallway directly before you put down the football. So basically, also while we're reading documents, we do exactly the same thing, right? You know, we search for the keywords that might be indicative of the answer, and then we step forward and backward as this. So an aside to this is that this is actually something that is kind of a traditional AI problem. This is something that you would have learned in any AI course when AI was still like in the 1990s or something, when AI was still a bad word and machine learning was the thing that you wanted to be doing if you were the cool kid with the math. So AI models have all kinds of things like reasoning with first order logic and various things like this. So there's a really, really good book. This is, I read this book when I took, I had a long plane flight or something like that, and I was like, oh, I wish I knew more about semantics. And I read this book, and it's a really, really good introduction. It also has Prolog code along with it if you want to go in and implement all of their examples in Prolog. So, but basically, there's a lot of methods that we have, which basically you do a parse, a syntactic or semantic parse, and get first order logic representations. Then you have something called a tableau that basically adds information incrementally, resolves it based on co-reference, updates the state of various things, etc. So compared to the stuff that we could do with first order logic, if we could actually robustly generate first order logic representations, the stuff that I'm going to introduce with neural networks is relatively unsophisticated. Until I get to the very last slide in this section where they are doing something, sophisticated and very similar to this. So the first example of this is memory networks. So memory networks have timely because we just had Jason Weston here talk last Friday. But memory networks, basically what they do is they have a very rudimentary version of multi-step reasoning. And memory networks themselves are kind of a general formulation of models that access external memory through attention. And this paper gives a specific instantiation for document level QA. So in a specific QA model, you first do argmax attention. So you take the score of given x, which is your current state, and all your memory cells, I, which go from 1 to n, and you basically grab the memory cell that is the max here. So O1 is kind of your first step of using memory, of looking up things in your memory, and you might do this based on a query or whatever. So the thing that they do here is they have an additional argmax step to get the second element of memory conditioned on the first. So you basically take in your input and the first memory step and do a second step of attention. So it's basically like multiple steps of attention through your memory to look up things. And then in the end, you use both to get the answer. So you use the 2 steps of memory. So this is interesting because it can do exactly what I mentioned before, right? First you attend to the football. You see the football's important, then you attend to John. You see John's important, and then based on John, you then attend to whatever else. So hopefully, by the time we've gotten to this part in the class, everybody in the class will look at argmax and say, ooh, I don't want to have that in my model. Hopefully, if you say, ooh, I do want to have that in my model, then, you know, maybe you can't be helped, but so the next obvious thing to do is to soften the argmax. So instead of using the argmax, you use a standard softmax attention, and then they also have multiple layers of this. So you have you have basically multiple layers of attention where you do attention and then step through, do attention, and step to the next one, do attention, then step to the next one, etc. So we have multi-step reasoning here. So here, I guess we have 3 levels. In the previous one, we had 2 levels, right? So here we use 2 in the output. Here we're using 3 in the output. So we have a natural question, which is when do we stop reasoning? When do we stop making multiple hops over memory or whatever else? So the most common way is to just do a fixed number of steps. So you step through a fixed number of time, like 2 or 3. This is, pretty, I guess this could be pretty sufficient because basically, if you don't need 3 steps of attention, then maybe you just ignore the last 2 steps. But more, there's also methods that basically, when they attend to a stop reasoning symbol, they stop reasoning. So you have a special kind of null symbol in your memory that when you attend to that, then you stop. And you can also have an explicit stop reasoning predictor. So you can also have a separate step that basically says, should I stop now or should I continue? So I think, basically either of these would be fine. But both of these papers, or particularly the second paper, show that it's kind of useful to have this as opposed to just having a fixed number of steps. Are there any questions so far? Yeah.
So how do the learn this predictor, given that this information is not directly?
So I guess if I remember correctly, the second one basically, I'm trying to remember the exact training objective for this because I read it a little while ago, but if I remember, it was basically masking out the memory and not using it if you stopped reasoning. And then the second one, I think they trained it with reinforce, basically. So when do we stop? I might be mixing them up, or I might be wrong about the second one, but I'm pretty sure that the third one here did use reinforce. Any other questions? This is something that's actually really easy to do without reinforce, though, because all you need to do is you need to have a mask, and you use if you stop reasoning, then you just use the one where you stopped reasoning. So another very yeah.
So in the case of the memory nets, how did they actually go through the argmax? Did they use reinforce or?
Okay, so that's a good question. So how did they go through the argmax? As far as I can tell, they just ignored the fact that this was a problem. this scoring function had other feedback, like which memory cell do you want to use? I believe they input the score in their final decision function as well. So as long as you have some sort of feedback to this scoring function, then you don't necessarily need to use reinforce or something like that. So an example of this is attention with a hard threshold. So if you do attention with a hard threshold, where you take the top 5 and run attention over the top 5, and then you just zero out everything else, then you can still learn this, right? Because you're still getting feedback from within the top 5. What you can't do is you can't do hard attention with the top 1, which is actually what they're doing here. So that's why it's a little bit strange. But this was before attention was a big thing. And obviously, if attention had already been a big thing, they would just use attention. Any other questions? So another interesting thing is course-defined question answering. So there's a couple instantiations of this, but the basic idea is you have this big data set that you want to use, and then based on this big data set, you want to pick out the relevant information, then use that relevant information to answer your questions. So the basic idea is you first decide which sentence to cover, and then reason over that particular sentence. So you have this sentence selection model that takes the query and decides which sentences in a document you should be using to answer the question. That gives you a summary of the document. And then based on this summary, you do answer generation with something like an RNN. So the good thing about this is if you have a really expensive model to do answer generation, you don't want to run it on the whole document because that would be prohibitively slow. But if you run it on only a subset of the sentences, you can use a complicated model. It's no problem. So the nice thing about this is this was also trained with reinforcement learning. This is something where you do have to use something like reinforcement learning because you don't want to be running your heavy answer generation RNN on this all the time. This is also kind of a variety of multi-hop reasoning if you think about it, because you're taking the document summary. There's also work on retrieval plus QA, which basically, instead of taking a document and taking the sentence from the document, instead takes full documents from Wikipedia and then tries to answer questions over these documents. This one actually wasn't trained jointly, as far as I could tell. This one was basically, it was using Lucene to look up documents and then using those documents to answer questions. So kind of, this one up here is the more sophisticated method, but only works on smaller documents, and this one works on Wikipedia scale. So an obvious next interesting thing would be, could you train a retrieval model that does much better than Lucene, for example, to do document level or do question answering over something like Wikipedia or the whole web. Okay. So now I'm going to get back to the kind of traditional AI thing. This is a really cool paper, but it's really scary, as you can tell from the graph or from the figure. So basically, what this is doing is it's called differential theorem proving. And the idea is that if you look back at the traditional AI methods for doing this sort of reasoning, basically they're taking these first order logic representations that we have, and they're doing reasoning over these first order logic representations that where you basically match the knowledge that you have, and then you match the rules or the theorems or the facts that you have in your knowledge base and then you use this to answer questions about whether your original proposition was true or not. And you could use this for question answering. You can use it for whatever else. So within this, how many people have taken like computational semantics or something like this? Okay. Yeah, it's not a lot of people, but basically, let's say we have a theorem prover, or let's say we have a theorem that's basically A or B and C. So the way we prove this is we basically write a for loop. And we write a for loop that tries to prove A. And if we can't prove A, then we try to prove B and C, because it's an or statement, right? Then if when we try to prove B and C, we then have a recursive step where we try to prove B and we try to prove C, and if either of them fail, then we get the rest. So the most important thing here is essentially something called unification. So unification, what this is doing is it's attempting to match together facts or predicates with other things, other facts or predicates in our knowledge base. And if you had, this is actually the whole idea of what Prolog is. Prolog is a programming language that was essentially written to make this very easy to do. It has a backend that does unification for you, etc. But the problem is, obviously, if you get all of your predicates right, all of your predicates are provable, then it's very easy to do this unification. It takes time, but you can get an answer yes or no about whether this theorem is correct or not. But the difficulty becomes when you have father of and parent of, for example. Father of and parent of, unless you have information about this relation, which entails which, etc., it becomes very difficult to say whether father of somebody entails parent of, whether these basically mean the same thing. So unification in a traditional system would fail in this situation, because these are different predicates, unless you had some sort of augmented representation, which is obviously very hard to do on a very large knowledge base. So the idea here is that you, in addition to having, when you do unification, basically you do unification in embedding space. So you have embeddings for the father of relation, you have embeddings for the parent of relation, you have embeddings for the mother of relation. And when you go to unify and you try to figure out whether these predicates are the same or whether they entail each other or not, you do this in embedding space. And the closer together they are, all the various elements of each of these are in embedding space, the better you do. The higher score this gets. And then what you try to do is, the way you train this model is basically you have real facts and you also have fake facts, or real news and fake news. And you want to optimize the embeddings in your model so that the real facts get a higher score than the fake facts. So you search, you do the search according to your traditional kind of Prolog, theorem prover. And anytime when you can prove a fake fact with a higher probability than your real fact, you penalize that and you raise the score of your real fact. So it's kind of a margin-based, it's essentially a margin-based training objective. This is a structured prediction problem where you're walking through the structure. So I think this is really nice. If you read the computational semantics book first and then read this paper, it's like, wow, this is awesome. If you don't read the computational semantics book first, you might be a little bit intimidated by the paper. But one important thing to mention here is that they're using this for knowledge-based completion. So this is also similar to the more simple, like soft logic rules thing that I talked about last time. And notably, they're not doing it for something like machine reading. If you look at the computational semantics work here, this was all very much about machine reading. You read, you get a logical form, you get all the facts, and then you prove whether your question is true or not, or you prove the entity in your question. So I think it'd be really cool if, number one, you could use this for something like machine reading, and number two, if you could show that it actually scaled up to like real hard machine reading problems. Yeah.
When you say fake, do you mean things that are unprovable or things that are actually false? Such that
You have so I guess you have a knowledge base, and if you can prove relations between entities that don't exist in the knowledge base, then that's considered a bad thing. So you sample an entity and another entity that are not in a relation. Of course, it's kind of hard to say whether things are not in a relation because the knowledge base is always incomplete, but that's the training objective they're using. Yeah.
What are the trainable parameters of this model?
So this is actually a really simple model. The trainable parameters are basically, if I remember correctly, just the embeddings of the entities and the relations. So it's not even really a neural model. It's a kind of embedding based model that doesn't have any nonlinear components.
And you're not back propagating through this entire unification process, are you?
Yeah, I guess in a way you are, but I don't know whether you even need to call it backprop or not based on how simple the model is. But you could call it backprop if you wanted to, I guess. So of course, you could define your score function in other ways. You could easily backprop through this whole process if your decisions in the next step were dependent on your decisions in the previous step. But as far as I could tell from reading the paper, that was not the case. So basically, you only have independent decisions. So you don't actually need to backprop through the whole thing. You just need to like update the parameters of each individual decision.
One more thing.
Yeah.
So how do you assign partial credit? For example, some of the steps might be correct, but right at the end you may have made a mistake. For the wrong factors.
Well, the short answer is you don't. The long answer is if your distractor, like the thing that caused you to get the wrong answer, is very similar to the thing that caused you to get the right answer, obviously the gradients for the things that are the same cancel out. So you would only be assigning gradients to the things that didn't cancel out. So I actually don't remember. I don't remember how they created their distractors well enough to say whether that happens a lot or not. But yeah. Anything else? So I think one thing is that actually neural network models are not super good at multi-step reasoning, despite the fact that they seem to be doing pretty well at stuff like SQuAD. Stuff like SQuAD, you can get pretty far with template matching. I think stuff like this or some kind of simplified version of this is actually is a pretty interesting direction, personally. So I've been giving enough of these that I don't know whether it's super necessary to do it again, but I'll give yet another caveat about data sets because there's a lot of papers in this area. So all data sets have their biases. So no matter the task, data bias matters, like domain bias, simplifications. In particular, for reading comprehension, real large-scale data sets are hard to come by. And data sets from weak supervision have not necessarily been vetted appropriately. So one case study in the baby data set is automatically generated synthetic text is aimed at evaluating whether a model can learn certain characteristics of language. So these are these really simple things like this. I think they spurred some interest in NLP problems in machine learning, which I think is a really good thing. But a lot of the problem is a lot of the kind of machine learning papers evaluate only on this extremely simplified data set and then claim about ability to learn language. So for extra credit, for extra credit, you can write a Prolog solver for, sorry, I misspelled that, but it's Prolog solver for baby. And if you write a Prolog solver that can solve all the baby questions, I'll give you points. I don't know how many because I think this would be this would take a significant amount of effort. But you know, I'm pretty sure that if you spent a month on this, you could easily solve all of these, and it would generalize much better than any neural model that you. So another one is on kind of like synthetically automatically generated data sets. So this is a famous examination of the CNN Daily Mail data set. So even synthetically created real data sets have problems. So for example, the CNN Daily Mail data set revealed very few sentences required any sort of reasoning. And many were difficult due to anonymization or wrong preprocessing. So there were a bunch of categories. On many of the ones you could basically solve by just doing an exact match over the data. So these are super easy ones. Another 41% could be solved by like simply paraphrasing words and finding the answer. Other ones are kind of partial clues in the data set based on common sense knowledge, where you can basically locate the thing that's talking about the same topic, and then the closest entity is the correct one. And then 2% required some sort of multi-sentence reasoning. And kind of the idea of this data set was it was supposed to be a machine reading data set that you would read through, you would understand multiple sentences and come up with an answer based on this, but unfortunately only 2% of the examples actually required this. Then another 8% of the examples were impossible to solve because of co-reference errors. So if you looked at the original text and the entities, co-ref failed, and because of this you couldn't answer the question. Another 6% were ambiguous or hard. Sorry, I don't have an example here, but one example was, and then entity 215, entity 320, entity 75, and entity 63 went to Paris. And it's like, X went to Paris was the question. So it's like, you've got 1 out of 4. Take your best guess, and then the second entity was the one that happened to be the one in the question. So I think it's very important to look at your data set to see whether you can actually solve it, which is why I emphasized error analysis so much in the assignments for this class. Another very nice example for Squad particular is this paper on adversarial examples in machine reading. And basically what they do is they add a sentence or word string specifically designed to distract the model, which drops the accuracy of state-of-the-art models from 81 to 46, basically. And so the way they do this is they have what city did Tesla move to in 1880? So they basically replaced, or they basically mutated the question. Then they added a fake answer, and stuck it on the end of the document. And most of the time, this fools the machine reading system to answer the entity on the end of the document. So sentences at the end of the document tend to be very important. If it exactly matches the question, exact match is a very strong indicator that it's correct. So you just replace the entities and come up with a fake answer, and then the system gets fooled most of the time. So what this is demonstrating, I guess, is that these systems are looking for pattern matches, and they're very good at doing that, but they're not, actually reasoning. So coming up with a model that doesn't, it's easy also to say, okay, now I'm going to train my model by adding these examples to my training set. And of course, that's going to do better. You're training your model to be robust to this. But I think the more interesting thing would be, can you come up with a model that is robust to this even without specifically training on these examples? And that would be a model that you can really say is reasoning. Yeah, I guess I can mention that recently in the past 6 months or so, there's a whole cottage industry of taking a popular data set and finding problems with it. So you can see a lot of other papers in this vein as well. Like for natural language inference, basically you take the output, you take the hypothesis, and then you run a classifier over only the hypothesis, and you can get high accuracy, et cetera. So think about this when you're choosing your data sets, I guess, is the point. Okay, so that's all I have for today. Are there any other questions or discussions? Anything people think maybe I missed that you should talk about? Okay, I'll finish up.